In Chapter 7, we're going to talk about energy. Energy is another one of those words that we think we know what energy means. But then if I said, tell me what energy is, it's kind of hard to actually describe it. Physicists consider energy the ability to do work, the ability to change yourself or to change your environment. So we'll start with looking at work. Work is a transfer of energy. That's a little bit different too than what you probably think of work as. You think of work as being any time you exert yourself, whether it's mental work, mental exertion, or whether it's physical work or physical exertion. But in physics, work requires a force that's applied through a distance. In terms of math, it looks like this. Work equals force times distance. And that's what our formula looks like. We know that we measure force in newtons and we measure distance in meters. If we multiply newtons times meters, we get a new unit that we call joules. All forms of work and energy and even heat are measured in joules. So our SI unit is the joule, capital J. Really important when you look at this formula, a couple things will come to mind. First of all, if I push on this wall really hard as I can, I just push and push and push, even if I work up a great big sweat pushing, if the wall does not move, no work was done on the wall because that distance would be zero. The other thing we need to understand is if a force does work, the object moves in the direction of the force. Okay? If you see something moving but the force doesn't point in that direction, then that's not the force that's doing the work. For example, if I have this calculator in my hand, gravity's pushing down and I'm pushing up, so the calculator stays right here. Now remember, gravity points down. If I move this calculator sideways, gravity is obviously not the force doing the work. So the work done by gravity would be absolutely zero. The work done by me pushing up also absolutely zero. In fact, when I do this, the force that's doing the work is actually static friction. The friction, no force between my hand and the calculator is the reason why it moves. Another important idea that we want to understand about work is that it is a scalar, which means work does not have a direction. I know I just said the force has a direction and the distance you move has a direction, but work itself does not have a direction. If you do 1,500 joules of work, you don't do 1,500 joules of work up or down. Energy of all forms, whether it's work or heat, does not have a direction. Energy is a scalar quantity. Let's do an example. Let's suppose we have a 200 Newton mass that's lifted to a height of 3 meters. Anytime you lift something, the amount of force you have to apply is equal to the weight of whatever it is you're lifting. So if I lift a 200 Newton mass or object, I'm going to have to exert a force of 200 newtons to lift it. I have to overcome gravity. So our work, which is force times distance, will be 200 newtons times a distance of 3 meters is going to equal 600 Newton meters. But I just told you, we don't call it Newton meters. We call it joules. Closely related to the idea of work is another physics concept called power. I'm going to leave that problem right up there. Power tells us how quickly work is being done. If I have 2 students and one does 20 problems in an hour and another student can do 20 problems in 15 minutes, well, they're doing the same amount of work. They're both doing 20 problems, but the person who can do it quickly would be considered to be more powerful. So power is equal to work divided by time. So power is work divided by time. We know work is going to be in joules, time is going to be in seconds, and that's going to give us another new unit. Let's say we have a 200 Newton mass lifted to a height of 3 meters, and we add a little more in 4 seconds. But we already calculated the work. We said the work was 600 joules. 200 newtons to a height of 3 meters is 600 joules, and the time is 4 seconds. So our power, if I do 600 divided by 4, would be 150 joules per second. It tells us how quickly we are using energy or doing work, how many joules per second. But we do have another unit for that. That is called a watt. Okay, I just want to give you a little bit of a warning. We often use a capital W for work. We all use a lowercase w for weight, but we also use a capital W for watts. So if you see something like 150 with a capital, that has to be 150 watts. So just be careful. A lot of times I'll try to write out the words. I'm not going to try and trick you with that, but I know W is used for a lot of things. Besides the watts, you will often see kilowatts, which means 1,000 watts. Or you may see horsepower. 1 horsepower is 746 watts. So a watt is a fairly small unit of power. However, it's one you're familiar with. If you buy a 60-watt light bulb, it uses 60 joules of energy per second. If you buy a 40-watt light bulb, it only uses 40 joules per second. The result is a 60-watt light bulb is going to be brighter. If you buy a blow dryer for your hair, you probably can choose blow dryers that have power ratings of 1,600 watts. That's a pretty powerful one. You may be able to find one that only uses 800 watts. Well, it makes sense if you use one that's only 800 watts. It'll take twice as long to dry your hair because it's only using 800 joules of energy every second, as opposed to the 1600 watt, which is using 1600 joules of energy every second. Okay, let's go on now that we've got an understanding of work and power, and let's talk about energy. Energy is the ability to do work. By doing work, we mean the ability to change the environment in some way, or the ability of the object to change itself. An object has energy, just like an object can be said to have momentum. When you do work on an object, you transfer energy. And in particular, you give it mechanical energy. Okay? There's a couple of ways to do that. Probably should have written the word mechanical, but we'll talk about mechanical energy. There's two different types. So anytime there's a force doing work on an object, that object's going to gain some mechanical energy. It can gain kinetic energy. We usually abbreviate it KE. And that is simply energy due to motion. If I throw a baseball, when I pick it up to throw it, I'm applying force to the baseball over some period of distance. I'm doing work on it. And as a result of that, the baseball gains kinetic energy. If I happen to throw the baseball directly at my dining room window, you can really see it has energy because it can damage my window. It can change the environment around it. So objects in motion all have energy, and the type of energy due to the motion is kinetic energy. The other type of mechanical energy is potential energy. Potential energy is stored energy. And there's a couple of types of stored energy that we could talk about. The one we're going to talk about in this class the most is gravitational potential energy. Now, gravitational potential energy is energy that's gained every time you pick something up and you place it higher. I can give this brown marker that I don't need some gravitational potential energy simply by raising it up. If I let go now, it has more potential to change the environment than it did when it was lower. It can do more damage. Okay? You can think of a vase up on the top of a bookshelf. If a cat knocks the vase off, it's got energy. In fact, it has enough energy that when it falls and hits the ground, it can shatter because it had gravitational potential energy. The other type of potential energy that sometimes we talk about is elastic potential energy. That's energy that something has because it's been stretched or deformed, like a spring or a rubber band. So this is actually due to the shape of the object. Think rubber bands. There are other types of potential energy. These are types of mechanical potential energy. You can have stored chemical energy. You can have stored nuclear energy. You can have stored electrical energy in a battery. So there's lots of types of potential energy. So anytime energy is stored, we think of that being potential. Energy due to motion is kinetic. Like I say, we're going to talk primarily about kinetic and about gravitational potential energy. You can think of mechanical energy as being the sum of the kinetic energy and the potential energy. All right, let's stop and think about gravitational potential energy. GPE, gravitational potential energy. We know that in order to lift something and set it up high, we have to do work against gravity. And anytime we do work against gravity, the work done will be the force times the distance. But if we're doing work against gravity, we have to have a force equal to the weight of the object. So the work done against gravity is mg, that's my force. And the distance that we move it is usually measured as a height. How high did we pick it up? So mgh. That's work that we do against gravity. Okay? That's also the amount of gravitational potential energy that the object is going to gain. If I think about it, this marker has a certain amount of gravitational potential energy if I hold it right here. If I raise it up higher, it's gained more gravitational potential energy. The amount it gained was the height from here up to here. Okay? Really important to understand that really only changes in gravitational potential energy are important. There's no place where the gravitational potential energy is absolutely zero unless we were to go to like the center of the earth. Because if you think about it, I can think about how much energy it has relative to the table. If I drop it here. I could think about how much energy it has relative to the floor. I could drop it here. I'm on the second story of my house. I could open up this window that's right there, and I could drop it out the window and think about how much gravitational potential energy it has compared to the ground outside. So this height is really just how high above whatever surface you're comparing it to. It's always just relative. So gravitational potential energy is given by the formula mgh. Anytime you lift something up, you do this much work and it gains this much gravitational potential energy. When I pointed out earlier, it's really important. Only changes of height are important. So if you think about if there's a pickup truck here or something, and you're loading stuff into the back of this truck, well, here, let me just make it a platform. Here's a platform. If you pick a box up and you set it up here, it gains a change in height from here to here. The gravitational potential energy that it got is going to just be mgh. If you did the exact same thing, only you used a ramp to push that box up, it still gains this much gravitational potential energy. It's the change in height that's important. It really doesn't matter how it did that. If you think about a child climbing up the ladder to a slide, and they may climb up 8 feet straight up, they're going to gain an amount of gravitational potential energy equal to mgh, and then they may slide down the slide, and that slide might be 12 feet long. But the amount of gravitational potential energy that they lose is exactly equal to the same amount of potential energy that they had gained when they climbed the ladder. It really doesn't matter whether you climb up straight up the ladder to take the short way, or if you slide down the long way. Your change in gravitational potential energy, of course, straight up will be an increase, and down will be a decrease. But it's the same either way. Let's look at an example. I'm going to change the numbers from my PowerPoint, mainly just to give you some different numbers. Suppose that Jim has a 300 Newton crate, and he puts it in the back of a truck 1 meter above the ground, so that the height that he lifts it up is 1 meter. So if you wanted to draw a picture, it looks just like what we talked about a minute. This would be a height of 1 meter. And he takes this 300 newtons and he sets it right here. How much work did he do? Well, work is force times distance. That's mg times whatever the distance was, which in this case is the height. So mg is weight. We already know weight. It's 300 newtons. That's the force. 1 meter, 300 joules of work. That seems really easy. All right. But he had to use 300 newtons of force to lift it up and put it in the back of the truck. But Jim has a younger brother named Joe, and Joe said, I think it'll be easier to use a ramp. So what Joe did is he used this ramp. And this ramp was same 300 Newton box. The ramp was 4 meters long. He's going to push it a lot farther than Jim did. Jim only just picked it up and went 1 meter. But let's think about it. How much gravitational potential energy, this is Joe, how much gravitational potential energy does this box gain? Well, it gains mgh, which is going to be 300, that's mg, 1 meter, that tells me that Joe's box and Jim's box have the identical amount of gravitational potential energy, which means that Joe must have done the same amount of work. The amount of gravitational potential energy that something gains is the amount of work you did against gravity. So Joe did the same amount of work. Okay, let's think about this. We know work equals force times distance. So if Joe gave his box 300 joules of potential energy, and he used a distance of 4 meters, Joe didn't just move it 1 meter, he moved his 4 meters. That means Joe doesn't have to use as much force. If I do 300 divided by 4, I find out that the force that Joe used was 75 newtons. Notice how that plays off. Jim did, let's just look at force times distance. He did 300 newtons for 1 meter, and he accomplished 300 joules of work, gave it 300 joules of potential energy. Joe, on the other hand, did 75 newtons for 4 meters. He accomplished the same thing. Joe didn't do less work. Joe didn't do more work. He did the same amount of work. However, Joe did use less force, only 75 newtons, over a much longer distance. If you're really strong, you might say, I'd rather use 300 newtons and just move it 1 meter. But if you're like me, I probably can't apply as much force as some other people. I might rather use a ramp, which allows me to use less force over a longer distance. We're going to study in a few minutes that ramps are one type of simple machine. They don't decrease the amount of work that we do, but it did decrease the amount of force we had to use. Okay. Okay, we're going to call that part 1, and I'm going to come back and finish the rest of chapter 7 in just a few minutes.